Europe, 1943. High above a quilt of clouds, a formation of American B-17 bombers pushes toward Germany. The sky burns with streaks of orange tracers and black flak bursts. One of the bombers, Liberty Bell, takes a direct hit to its left wing. Fuel sprays out in a shimmering arc. Inside, the crew braces for the explosion they've seen take down so many others. But it doesn't come. The pilot glances at the pressure gauges, still holding steady. The smell of gasoline fades. The engines roar on. Against all odds, the bomber keeps climbing. Hours later, when the crippled aircraft limps back to its base in England, ground crews inspect it in disbelief. The fuel tank, pierced by cannon fire, is dry around the wound, sealed shut, as if the metal itself had healed. Across the Channel, German intelligence officers examine wreckage from downed American planes. Their engineers run their fingers over jagged holes surrounded by strange black material, layers of rubber and treated fabric that seem to swell when punctured. "What is this?" one asks quietly. It is the weapon they never expected. A tank that refuses to die. At the dawn of World War II, airplanes were as fragile as they were powerful. Their sleek frames and roaring engines inspired awe, but inside those aluminum shells lay their most lethal weakness: fuel. In the early years of the conflict, one bullet through a gas tank meant instant death. High-octane aviation fuel ignited with the smallest spark. A single incendiary round could turn a bomber into a flying fireball. Pilots didn't just fear enemy fighters, they feared their own fuel. The statistics were horrifying. In 1940, British and American air units recorded that nearly 60% of all aircraft lost in combat burned before they ever hit the ground. Crews rarely had time to bail out. In the Pacific, Japanese Zero fighters exploited this flaw mercilessly, diving on U.S. bombers and aiming directly for the wings, where fuel tanks sat exposed between the spars. Back in England, ground crews would sometimes watch returning aircraft stagger down onto the runway, leaking fuel like open wounds. The slightest spark from a braking wheel could set off a blaze. Mechanics wore wet rags on their shoulders to smother flames when repairing punctures. For every mission launched, men wondered if they were climbing into an aircraft or a coffin. The problem wasn't courage, it was chemistry. Aircraft fuel tanks of the 1930s were typically made from thin aluminum or simple rubber bladders, light enough for flight, but fatally brittle under gunfire. When a bullet tore through, the tank ruptured and air rushed in, mixing with vaporized gasoline to create a floating bomb. Engineers had tried patchwork solutions: armor plating, external fuel drums, protective coatings, but each added weight, reducing range and speed. A tank that could seal itself seemed like fantasy, and yet necessity has a way of bending the impossible. In 1940, after watching squadrons burn over Europe, the British Air Ministry began experimenting with an idea first conceived before the war: self-sealing fuel tanks. The principle was deceptively simple. If the outer layer of the tank could swell when exposed to fuel, it could close the puncture before oxygen reached it. The concept came from the natural expansion of raw rubber when soaked in. Gasoline. British scientists at firms like Dunlop and the Royal Aircraft Establishment began layering materials: vulcanized, rubber on the outside for durability, untreated rubber inside for expansion, and thin fabric sheets sandwiched in between. When a bullet entered the tank, the inner layer would absorb fuel, swell, and seal the hole tight. In 1941, the design reached operational aircraft, most notably on the Supermarine Spitfire and Hawker Hurricane. Pilots noticed the difference immediately. Planes that once burst into flames now limped home riddled with bullet holes, leaking but alive. Word spread across the Atlantic. American observers studying wrecked British aircraft at RAF bases realized what they were seeing: a quiet revolution in survivability. When the United States entered the war after Pearl Harbor, the need for such protection became urgent. American bombers and fighters would soon face long-range missions over enemy territory. Missions where a single hit could mean 10 men gone in a flash. The U.S. Army Air Forces and Navy began importing British self-sealing technology in 1942. But what America did next would astonish even the British engineers who pioneered it. Rather than simply copy the design, the United States decided to industrialize it. Rubber companies like Goodyear, Firestone, and Goodrich, along with chemical firms like DuPont, collaborated under wartime contracts to refine and mass-produce self-sealing tanks on an unprecedented scale. American chemists replaced scarce natural rubber with synthetic compounds like neoprene and Buna N, more heat-resistant and durable than anything used before. By mid-1942, production lines in Akron, Ohio, and Los Angeles were turning out thousands of these tanks every month. Flexible, bullet-resistant bladders lined with expanding layers that could heal under fire. And as they began to appear in aircraft across the Pacific and European fronts, something extraordinary happened. Pilots who once dreaded tracer fire began to trust their machines again. The difference between life and death was now measured in chemistry and in the silent, swelling heartbeat of rub. By 1942, the American aircraft industry was no longer just building machines, it was building resilience. Inside vast factories in California, Ohio, and New York, rows of workers assembled the invisible armor that would soon redefine aerial warfare. Each self-sealing fuel tank was hand-layered with precision: an outer shell of vulcanized rubber, a middle layer of treated fabric, and an inner lining made from raw, unvulcanized rubber that could swell when soaked in gasoline. When a bullet entered the tank, friction and pressure caused the outer layers to compress, while the inner raw rubber reacted chemically to the escaping fuel. It expanded, closing the hole like skin healing around a wound. In laboratory tests, engineers fired incendiary rounds directly into these tanks. The holes sealed within seconds, sometimes before the leaking fuel could even ignite. For pilots, it was more than a technical improvement. It was a psychological transformation. Until then, airmen had flown under constant fear that one hit would turn them into fire. But by 1943, that fear began to fade. Crews climbing into B-17 Flying Fortresses and P-47 Thunderbolts started to believe in their chances. They knew their tanks could take damage and still bring them home. The system wasn't perfect. A large-caliber round or direct cannon hit could still rupture a tank beyond repair. But for most encounters, machine gun fire, shrapnel, near misses, the self-sealing design worked with astonishing reliability. The Pacific War offered brutal proof. At Guadalcanal, Marine Corps F-4F Wildcats often returned from missions with dozens of holes in their fuselages and wings. Maintenance crews would remove the tanks, drain them, and find black rubber layers puffed outward where bullets had passed through, sealed tight. The smell of fuel, faint but contained, reports from the field stunned Washington. Commanders noted that self-sealing tanks had reduced aircraft fire losses by nearly 2/3 in just a year. In many squadrons, survival odds had flipped from hopeless to favorable. The War Department moved quickly. By late 1942, the technology became mandatory in every new combat aircraft. Fighters, bombers, even transport planes. The U.S. Army Air Forces made it clear, no airplane leaves the factory without protection. This rapid standardization represented something larger than engineering. It showed how America fought the war. When the British invented, the Americans multiplied. Factories once producing automobile tires and rubber gaskets now churned out complex fuel bladders by the thousands. Women technicians, many of them with no prior industrial experience, learned to weld seams and apply adhesive layers with surgical care. Each tank carried a small stamp, initials of the worker who made it, a silent signature beneath the wings of war. Behind the scenes, material scientists pushed the chemistry even further. Natural rubber supplies were dwindling due to Japan's conquest of Southeast Asia, so U.S. chemists adapted the self-sealing formula to synthetic rubber. The result was a tank even tougher under heat and pressure, perfectly suited for high-altitude bombers and tropical climates alike. In Germany, intelligence officers noticed something disturbing. Wrecks of American planes, when recovered, revealed tanks that were not standard aluminum or fabric. Instead, they found layered composites that resisted dissection. They recorded them in reports as foreign fuel protection of remarkable elasticity. At first, German engineers dismissed it as over-engineering, until Luftwaffe pilots began to complain that Allied aircraft refused to burn. The shift in aerial warfare was subtle, but monumental. A self-sealing tank didn't make an airplane invincible, but it bought seconds. And in aerial combat, seconds meant everything. Those extra moments could mean finishing a bombing run, clearing enemy territory, or reaching the sea to ditch instead of exploding mid-air. Thousands of lives were now measured not in luck, but in layers of rubber. By the end of 1943, American self-sealing fuel tanks had become an invisible symbol of the nation's technological doctrine. Simple ideas, mass-produced to perfection. And while Germany's engineers relied on precision metallurgy and aerodynamics, America had quietly mastered something far more elemental: survival through science. Every great innovation in war begins as desperation, and the self-sealing fuel tank was no different. What made it extraordinary was not just what it did, but what it represented: the merging of chemistry, industry, and human ingenuity in a moment when survival depended on invention. The brilliance of the self-sealing tank lay in its simplicity. It didn't require new alloys or exotic compounds. It relied on understanding how ordinary materials could behave in extraordinary ways. A standard design contained 4 key layers. The outer shell was vulcanized rubber, tough, heat-resistant, and protective. Beneath that lay a layer of treated cotton fabric that provided tensile strength. The next was the secret weapon: raw, unvulcanized rubber. When gasoline seeped into it, the layer expanded, swelling shut any puncture within seconds. Finally came an inner barrier, a thin film coated with neoprene or Buna-N synthetic rubber to prevent fuel from dissolving the rest of the structure. Each layer had a purpose. Together, they turned chemistry into armor. What truly shocked German engineers later wasn't the materials, they were familiar with all of them, but the scale and precision of the American process. In U.S. plants, every seam was bonded under heat and pressure to exact tolerances, producing bladders that could flex with aircraft motion and temperature. In tests conducted at Wright Field, engineers shot 30 and 50 caliber rounds through tanks filled with fuel. The results bordered on the miraculous. Within seconds, the holes vanished, the smell of gasoline faded, and the tanks held pressure. Some engineers joked that the rubber seemed almost alive. That living quality became the secret of American air superiority, not through brute armor, but through adaptive protection. On the battlefield, this invisible armor changed everything. Before self-sealing tanks, fighter pilots often carried a chilling nickname for their machines: flying lighters. A tracer strike in the right place could turn a cockpit into a torch. Many didn't wear parachutes at low altitude. There simply wasn't time. But once self-sealing technology was installed, the rhythm of combat shifted. Pilots began to fly more aggressively. They could dive deeper, press longer into combat zones, and climb higher after taking hits. The P-47 Thunderbolt, known for its rugged frame, became almost indestructible when fitted with self-sealing tanks. German pilots would hammer it with cannon fire only to watch it keep flying, smoke pouring from its tail, but engines still burning clean. The B-24 Liberator and B-17 Flying Fortress bombers benefited even more. Missions over Germany routinely lasted 8 hours or longer, exposing aircraft to flak and fighters. A non-sealing tank could turn a minor puncture into disaster. The new design gave crews a fighting chance. Reports from 8th Air Force maintenance units recorded bombers returning home with over 100 bullet holes. And unburned. Those saved seconds after impact translated directly into saved lives. Crews who once said silent prayers at takeoff now trusted their machines. Fear of fire, that silent shadow that haunted every flight, began to fade from memory. Tactically, it forced the enemy to waste ammunition. German fighters now needed more rounds to down a single bomber, more passes through defensive gunfire, more time in the kill zone. In air warfare, that imbalance was fatal. The self-sealing tank, though never seen in propaganda films or posters, was quietly doing what no weapon could: altering the psychology of flight. Technology only matters when it reaches the human heart. And for the men in those cockpits, it did. Many airmen didn't know exactly how the tanks worked. They just knew they worked. Pilots returned from missions in disbelief, finding bullet holes in wings that should have meant certain death. Mechanics would tap the sealed spots with a wrench and grin. "Closed up tight," they'd say. This invisible protection built confidence. A pilot who trusted his aircraft fought differently. Steadier, bolder, less distracted by fear. Morale surged. Letters from air crew to their families began mentioning the strange new technology. One B-24 gunner wrote home, "We got hit in the wing tank today. I smelled gas for a minute, then nothing. I think the plane fixed itself." That faith spread through squadrons like wildfire. Even superstition turned scientific. The men began to call their aircraft self-healers, as if they were alive. But it wasn't magic. It was the triumph of collaboration. Dozens of anonymous engineers, factory workers, and chemists had unknowingly saved the lives of men they'd never meet. Women at Goodyear plants layered sheets of rubber by hand, each one destined for an aircraft somewhere over Europe or the Pacific. Their fingerprints, sealed into the material, became part of the war's most unsung armor. In that sense, the self-sealing tank was more than technology. It was a bond between those who built and those who flew. Every sealed bullet hole, every aircraft that made it home on empty fuel and hope, was a testament to human connection under fire. And across the ocean, the Axis powers began to notice. By late 1943, German engineers and intelligence officers were growing uneasy. Luftwaffe pilots were reporting something that seemed impossible. American aircraft, especially the new P-47 Thunderbolts and B-17 bombers, were taking direct cannon hits to their wings and fuel tanks, and yet refused to burn. At first, Berlin dismissed the reports as exaggeration or luck. But as downed Allied aircraft were recovered and examined, the truth emerged. Inside their wings were fuel bladders, lined with strange layers of dark rubber and fabric, a structure unlike anything the ABVT Luftwaffe had ever used. Captured tanks were dissected at the Luftwaffe Technical Research Center in Rechlin. Engineers tried to reverse-engineer the material, boiling it in oil and soaking it in gasoline to test its reaction. They discovered that the inner layer expanded when in contact with fuel, effectively sealing small punctures. To the Germans, this was both impressive and humiliating. They had developed superb aircraft like the Messerschmitt Bf-109 and the Focke-Wulf FW-190, machines built with precision engineering and speed in mind. But they had overlooked survivability. Their fighters relied on speed and agility, not endurance, a philosophy that now seemed outdated. Reports filed to the Reich Air Ministry described the Discovery as eine bemerkenswerte Konstruktion, a remarkable construction, and urged further investigation. But it was too late. Germany's supply of rubber, both natural and synthetic, was dwindling fast under Allied bombing and naval blockades. Even if they could copy the design, they couldn't produce it on any meaningful scale. A captured American engineer later remarked, "The Germans had the science to understand it, but not the freedom or resources to make it." And in that contrast, innovation through collaboration versus isolation through control lay the essence of the war's industrial divide. The Allied secret wasn't just invention, it was replication. America could not only create the technology, but build it by the tens of thousands. Factories in Akron, Cleveland, Los Angeles, and Buffalo transformed overnight into self-sealing tank assembly lines. The process was intricate. Sheets of rubber were cut, layered, vulcanized, and sealed using massive heated presses. Workers, many of them women, measured tolerances by hand, stitching fabric layers like surgeons preparing lifelines. By 1944, these plants were producing over 20,000 self-sealing tanks per month. The system was so efficient that replacement tanks could be shipped anywhere in the world within weeks. This industrial flexibility was something Germany, with its fragmented wartime economy, could never match. Each American aircraft, from fighters to bombers, carried several of these tanks, flexible bladders that could bend with turbulence and heat. Even the P-51 Mustang, famed for its long-range escort missions deep into Germany, owed part of its success to them. Without self-sealing tanks, many Mustangs would never have survived the return journey home. Inside the production facilities, engineers continuously refined the design. New adhesives improved sealing time. Synthetic rubber blends increased fuel resistance. Every small enhancement multiplied across thousands of aircraft. In wartime memos, generals called it the quiet miracle. There were no headlines, no medals, no parades, yet every sortie, every raid, every mission across the English Channel depended on this invisible technology. It was victory by accumulation. Small advantages, replicated at scale, turning into unstoppable momentum. What made the self-sealing fuel tank remarkable was not just that it saved machines, it saved people. In a war often defined by destruction, this was a device built purely for preservation. Its purpose was not to kill, but to prevent death. In a sense, it represented a rare moral inversion, a weapon of mercy inside a world of fire. Every time a bomber limped home on sealed tanks, every time a pilot walked away from a mission that should have ended in flame, the philosophy behind Allied warfare deepened. Science in service of survival, not annihilation. This distinction mattered. It shaped how nations fought and what they fought for. Germany's engineering was built on control, the perfection of machines. America's engineering was built on resilience, the protection of life. Strategically, the technology's value went beyond combat. It influenced how Allied planners thought about endurance. If aircraft could survive longer, they could fly farther. Longer missions meant deeper strikes, and deeper strikes meant breaking the enemy's production capacity from within. The self-sealing tank, therefore, was not just a defensive measure. It was an enabler of offense. It allowed bombers to penetrate the German heartland and return. It made possible the relentless air campaigns that crippled Nazi industry and transportation. For the men who built it, it was an industrial masterpiece. For those who flew with it, it was faith made tangible. And for the German scientists who finally studied its remains, it was a revelation that the future of warfare would not belong to those who built the fastest planes, but to those who could make them endure. The era of fragile speed was over. The era of engineered survival had begun. Summer, 1943. The sky over Europe is burning. From airfields in England, Waves of American B-17 flying fortresses rise before dawn. 300 aircraft, silver silhouettes climbing into thin air. Their target, the heart of Nazi Germany's industrial empire. Ball-bearing factories, fuel depots, rail hubs. At 20,000 feet, flak bursts bloom like black flowers. The Luftwaffe strikes with precision. German fighters dive through the formations, 20mm cannon shells tearing through aluminum. In seconds, the air becomes chaos. Wings shearing off, engines aflame, smoke spiraling down through the clouds. Inside one of the bombers, Hell's Angel! A cannon shell slams into the left wing, puncturing the main fuel tank. The crew braces, waiting for the explosion that should follow. But it doesn't come. The fuel gushes briefly, then stops. The pressure gauge stabilizes. The engines keep humming. The pilot, stunned, grips the controls. "We're still flying," he mutters. They finish the bombing run, and hours later land battered but alive. On the ground, mechanics inspect the wing. The tank bears a jagged hole, the metal scorched around it, but sealed. The self-sealing layers have swollen tight, choking off the leak. The crew poses for a photograph beside the wound, proof that technology had just rewritten fate. Scenes like this played out across every front that year. In the Pacific, Marine corsairs returned from raids on Rabaul, with wings pocked by bullet holes, their tanks intact. At Bougainville, F-4F Wildcats landed on smoking runways, streaming oil but unburned. At Ploiești, American bombers penetrated walls of anti-aircraft fire. Half came back shredded, yet not one exploded from a fuel hit. These weren't isolated miracles. They were the result of chemistry and design working perfectly in battle. A U.S. Army Air Forces report from 1944 quantified the miracle. Aircraft equipped with self-sealing tanks had fire loss rates below 10%, compared to over 50% in non-protected models. The difference was life or death. The system had proven itself not in laboratories, but in hell. For every mission that returned, word spread among air crews. Pilots no longer flinched at tracer rounds streaking past the wings. They could focus on flying, not dying. "Confidence," wrote one squadron commander, "is the rarest ammunition." The tanks gave it back to us. Even ground crews began to revere the design. Mechanics developed rituals, tapping the tanks with wrenches before flight, as if greeting old friends. They'd run their hands over sealed punctures and whisper, "She did it again." The self-sealing tank wasn't glamorous like a new fighter design or radar system. It didn't roar, didn't shine. It was invisible. And that was its power. The Germans began to notice. Pilots of the Jagdgeschwader 26 fighter wing, after repeated engagements over France, reported frustration. Their cannon shells, designed to ignite Allied fuel tanks, often failed to cause fires. "Their wings don't burn," one pilot wrote. "They keep coming." The Luftwaffe command ordered immediate analysis of captured Allied aircraft. Teams at Rechlin and Göttingen studied the black-layered fuel cells removed from downed bombers. Reports described elastic armor and hydro-reactive vulcanization, phrases that hinted at bewilderment as much as respect. To them, it was almost alchemy, a tank that healed itself faster than flames could spread. In October 1943, a German technical officer summarized it bluntly, "The Americans have weaponized chemistry." That statement echoed the deeper realization spreading through German high command, that industrial science, not firepower, would decide the war. While Germany's engineers still prized mechanical perfection, the fastest engines, the most advanced aerodynamics, the United States had quietly mastered the art of resilience, and in the skies above Europe, that resilience was now invincible. By winter, Allied bomber survival rates had improved so dramatically that daylight raids over Germany, once considered suicide, became standard practice. The crews flying them were no longer gambling with fate. They were flying behind layers of American chemistry, innovation, and faith. The war in the air was no longer just about who could shoot straighter. It was about who could endure longer, and in that battle of endurance, the self-sealing fuel tank had turned the tide.